I received a CNC machine Type 3018 Pro from Mostix. I accepted the offer to test this CNC because I wanted to check if I could do isolation milling with that machine, an idea I had in mind for a long time. With a working area of 30x18x4cm, the 1380 Pro can process standard board sizes while still being compact in the overall dimensions. As extras, there are a unit for offline operation or remote control and a laser module available, which I also received with the package. The frame is composed of a mix of aluminum profiles and plastic parts and, with a size of 44x37x31cm, fits on any workbench or desk. The 3018 Pro is delivered well packaged with all tools required for assembly and a printed, easy to understand instruction with many detailed drawings and photos. You don't need too high skills to put all parts together. I needed half a day for the assembly, with most of the time passing by for making lots of photos during that process. The cabling is also done very quickly, only the 3 stepper motors and the spindle have to be connected to the circuit board on the back of the machine via plugs with reverse polarity. If you want to get a deeper insight into the steps needed, you can find the construction stage photos on my website as download package. An ATmega 328P like the one installed on the Arduino boards is the central processing unit, and Gabel in version 1.1 runs on the chip. The on-off switch on the circuit board at the backside of the frame is out of reach in an emergency situation, which is why it is advisable to use a switchable socket in front of the machine. The Y-axis moves the table back and forth by 18cm and it is supported by 10mm round bars. The 8mm diameter spindles of all 3 axes are firmly connected to the stepper motors via aluminum adapters. The longitudinal forces are therefore directed to the ball bearings of these motors. Since the CNC is not designed for metalworking, I think this is a very good solution to get a low backlash drive. The lead nuts are simple press nuts, and so they come with a bit of backlash. A combination of a helical spring and a second nut is used to compensate for this. This of course only works as long as the longitudinal force during milling is smaller than the force the spring delivers, which is true only for rather low forces. The X and Z axis work with the same principle. The X-axis moves up to 30cm to the left or right. This axis is also guided along 10mm round rods. "8mm rods are used for the Z-axis, as this only moves a little more than 4cm up or down. I really like that all 3 axes can be operated manually using hand wheels. The cutting tool is mounted with an ER11 collet having an insert for 3.175mm shafts. That insert must first be snapped into the corresponding nut before the tool can be inserted. The CNC comes with V-bits that can be used for engraving or cutting work. A DC motor with the ER11 collet mounted on the shaft is used as spindle drive. It's simple physics that such a long lever can't grant good runout. With the naked eye you can see a slight wobble of the collet. Data can be transmitted to the CNC either via USB interface or via SD card and the remote control module that is available as an extra. The stiffness of the frame is okay, but not perfect. The rather long lever from the round rods guiding the X-axis to the tip of the cutting tool causes the whole construction to twist visibly whenever you push a bit stronger. All in all, the mechanics is okay for the price range, and to be honest, the manufacturer does not advertise the 3018 Pro for metalworking. In order not to mess up expensive circuit boards, I started a first test run with a plastic plate. To fasten the workpiece on the grooved plate, screws with swing nuts and metal plates are included. A wooden plate should always be attached under the workpiece to prevent the milling cutter from diving into the aluminum of the table, which will inevitably break the tool. I use the remote control to move the spindle to the 0 point, which corner it is depends on the settings in the CAD software used, for this file it is at the bottom left. Now I carefully move the Z-axis with the handwheel down so far that the cutter almost touches the workpiece. A piece of paper helps to find this point. The file to be processed is in G-code format on an SD card, and the extra module is used to forward the data to the CNC with no need for a PC. When removing material with a milling cutter, frictional heat is generated. To prevent the plastic from melting, I made curbs out of modeling clay and filled the resulting basin with water. The outlines of my mascot are engraved by the 3018 Pro with a total depth of 0.6mm. The engraving is done after about 20 minutes. I really like the result of this first quick test. Now let's come to the intended use, the isolation milling of circuit boards. The milled grooves should be as narrow as possible. The depth at which the tip of the V-bit dives into the copper-coated plate during the milling process should be constant. To achieve this, the height of the plate is measured at various points using the milling cutter itself as sensor. Ground is connected to the copper plate and the V-bit is connected to a GPIO on a Raspberry Pi via the motor and a series resistor, seen here with my Pi top. As soon as the cutter tip touches the copper plate, the GPIO pin is pulled to ground and the current height of the Z-axis is stored. The Raspberry Pi automatically moves to all points in a grid defined by software. I have written a Python script for this purpose. As a really hard test, I put another wooden plate under the circuit board on the left side and only fixed 3 corners of the board to the table. Both the scratches on the copper board, as well as the broken tip of the V-bit indicate that error-free software does not exist, which is particularly true for early versions. When leveling the surface, the Z-axis moves down faster in the first pass, stops when it comes into contact with the copper plate and immediately moves back up half a millimeter. In the second pass, the Z-axis is lowered slowly. You can see that the loose corner of the circuit board visibly bends down in the first pass. An effect that is much less to see in the second run. Ideally, the circuit board should be as flat as can be on the routing table, which is usually done by special mounts, double-sided tape and things like that, but the purpose of this test is to only use what is inside the package. After the surface is leveled this way, the script can do a test run and drive the spindle along an ellipse with the maximum values of the circuit board to be milled. The tip of the V-bit is held at a height of 0.2mm above the surface. It can be seen that this works well, even with the extremely poorly attached circuit board. In the long shot you can see how the handwheel of the Z-axis turns while the software compensates for the inclined plane. Once the circuit board has been leveled, the script starts the milling process. My first attempts to mill a circuit board have failed, but giving up is only for the faint-hearted. The solution I came up with is that the cut to the final depth is done in more than just one run. In the first pass, the copper coating is only scratched. It can be seen that the milling cutter dives into the material to different degrees. The boards I purchased for my first tests are the cheapest I could get. The surface has visible ripples, which means that the cutter removes more or less only the tips of those ripples in the first pass. The height measurement of the surface with a grid of 20mm intervals of course did not record the ripples. It should also be taken into account that the copper coating is only 35 micrometers, which is 0.035mm thick, and you cannot seriously expect that the mechanics of an inexpensive CNC is free from backlash of this magnitude. Overall, however, the 3018 Pro meets the given coordinates with a sufficiently high degree of precision. The grooves are milled straight. The conversion of the Gerber files created with KiCad to G-code was done by the software PCB to G-code. My script reads the files generated this way and adds some extra functions. After the first pass, the tracks are not yet isolated from the rest of the copper coating. After each pass, the script asks whether the file should be processed again, with the cutter being lowered a bit more. This question must be answered with yes for so long. Until finally all the grooves are milled deep enough to get insulated traces all over the board. After that, the holes are drilled in the next pass. I use a standard 1mm drill that I had on stock. The second nut and the corresponding ER11 insert for the 1mm shaft also were in my workshop. The script first places holes in all 4 corners of the board. Oops, still a bug in the software, the first hole is drilled with a too high speed. Did I mention that the script is being tested during the video recording? The close-up shows that the drill dances a little on the surface before it dives into the material of the circuit board. As already mentioned, the runout of the spindle is not perfect and the long, thin drill bends easily, which leads to the observed inaccuracy. All in all, however, the 124 holes were made with a sufficient precision. With that, the bottom of the board is finished. The milled grooves have really smooth edges, the V-bit cuts through the material without tearing off the edges of the copper coating. For the reasons mentioned, the holes are not as nicely centered as they should be. A good milling cutter should deliver better results. The copper around 2 holes was ripped off during drilling, but this is due to the fact that these are pins without an electrical connection to any path. This error is therefore irrelevant for the function of the board. I am happy with the result, the board will work as it came out of the machine, there is no need for any rework. The next step is to label the top using the 5.5W laser module. This device is connected to the electronics of the CNC with a separate control unit for which only one additional cable is required. The laser replaces the spindle. The 3018 Pro has no protective cover that prevents you from looking directly into the laser light, so wearing protective goggles is mandatory. The script now moves the laser head to the lower left corner of the board and turns the laser on to just 1% of its maximum power. The laser beam must now be focused on the surface, and afterwards the laser point must be moved to the lower left hole using the hand wheels. After this position is confirmed with enter, the laser now moves to the top right corner. Here, if needed, the board must now be moved so that the laser beam hits the second hole too. The machine is then ready to laser the markings, and this process starts after pressing enter. In addition to the laser light, the resulting fumes are harmful to health. The process should take place near an open window or outdoors. I moved into my garage with the door open. Lasering the surface did not work the first time either. The problem is that the board material first melts and evaporates, but then carbonizes and so turns black. From this point on, the material absorbs a lot more of the laser light, which suddenly burns a lot more plastic, resulting in an irregular engraving. Various tests with different laser powers have shown that the point from vaporization to charring is difficult to hit. To solve the problem, I don't work with a constant laser beam, but trigger short pulses with a movement of 1/10 of a millimeter between two laser bursts. In addition, I sanded the surface of the circuit board so that the laser light is better absorbed. The smoke traces around the lasered lines make the result not look that good. But after they have been removed with sandpaper, the lettering can be clearly read. The circuit board is finished, and I am completely satisfied with this first result. So I switched on my good old soldering iron to start assembling. Since I was using a single-sided circuit board, some connections to the lower copper tracks are made via bridges on the top. The soldering worked without any problems, and the final result looks like this. It is an H-bridge that is controlled by a tiny 85 microcontroller. The microcontroller can receive commands via an interface in the form of pulse width signals or, as can be seen here, read the voltage on a potentiometer. Thanks to the software running on the chip, the motor also works autonomously. My first attempt to manufacture a circuit board out of the box with the Mostix CNC 3018 Pro can therefore be described as successful. The machine can perform the necessary steps with a sufficiently high level of precision without any modifications. I really like the result. Anyone who enjoys experimenting will be able to improve the results. At least I have caught fire and will certainly use the 3018 Pro more frequently for future projects to make circuit boards. Milling plastics or wood, as well as the possibility of working with the laser module, expand the range of uses of the relatively inexpensive machine. If you want to take a closer look at the mechanics as well as the circuit board I've made, you will find many photos in high resolution on my pages. Have a click. Thanks for watching, and I'll be back.